Okay, so let's just summarize this. That this is the problem. Can you see my screen?
Yes.
Yes, Dr. Roy.
Okay, so quickly I'm just summarizing it. That this is the problem that was given. That the acetone at a flow rate of 20 kg per second. 20 second per second is to be heated from 10 degree to 30 degree Celsius with therminol, which is available at 100 degrees Celsius with a flow rate of 25. And then you have to select shell and tube heat exchanger for this application. Okay. So the exchanger size is not given. We have to select it. So we are following the step-by-step method. And so first of all, what we did, we collected the properties. So the collecting the properties is same as we did in double pipe heat exchanger. So we write down the properties of acetone and we write down the properties of therminol. Okay. So then after this, we calculated what is R. This is the capacity ratio, and what is S. So we follow the formula for R and S that we have for R and S. That where is that formula? I will show you. Yeah, here this is. So you can see that the formula for R and S. So R capacity ratio, S this formula to find out the F. F either you can find from this chart or you can find from this formula. So we find out this and then we listed here. So the F value is indicating that it is greater than 0.75. So that means if the F is greater than 75, which indicate that the shell and tube heat exchangers is good for this application. Okay, fine. Now we are going to select the heat exchanger. So for the heat exchanger selection, we are going to the tables where the heat exchanger size is given. So here are some tables where the heat exchanger size is given. So let's see these tables here. This is table number 1, table 2, 3, and table 4, 5. There are 5 tables. So in these tables, at the top, what is given is the outer diameter of the tube, 1 inch, the pitch of the tube, 1 1/4 inch, and the triangular distribution. So there are 3 things it is given: outer diameter of the tube, pitch of the tube, and its distribution. So these things are given in 5 tables, different tables. And corresponding, we have the shell size. What is the shell outer diameter, inner diameter of the shell, and how many number of passes. So depending upon the passes, there are number of tubes. Okay. So we are free to choose from any table, any size from anywhere within these 5 tables. So, but we have chosen this size. The inner diameter of the shell is 336.6 millimeter. The tube outer diameter is 3 by 4 inch, and 1 inch is the pitch, and the square is the distribution. So this is what we choosing. So, okay. So, and the same thing we have noted down in the Excel file, that this is our outer diameter, or we call it shell diameter. This is our outer diameter of the tube, and this is the pitch of the tube. You see my screen? Can you see my screen, right?
Yes, Dr. Roy, can.
Okay, so this is our pitch, and this is the number of tubes. So the number of tubes and this thing, we got it from here, that we selected this one. So we selected the 2 pass, and the number of tubes are 90. So the 2 passes, number of tubes are 90, and shell diameter is this. Okay. So, and the length is given in the problem, that the length is 2 meter.
Doctor.
Okay. So we have the tube outer diameter. How do we get the tube inner diameter? Yes. Yes.
From where we got the inner diameter of the tube?
Yeah, I'm coming to that point. inner diameter. How do we get this, right? So the inner diameter, we need to select, we need to select that what is the BWG. We need to choose BWG. So here we have the several BWG, like this is for the tube outer diameter is 3/4, and this is for when the tube outer diameter is 1 inch or 25.4 millimeter. Okay, so in our case it is 3/4 inch, so this is applicable for us. So what BWG we choose, so it is depends upon the requirement strength. You have to carry out the strength analysis, that what thickness of the tube you need. So what, which is not in our scope, so we are not doing this. So we are selecting the 13 as the BWG. So for 13 BWG, if my outer diameter is 19.1 millimeter, then what is my inner diameter? Inner diameter is 14.2 millimeter. Is it clear? So my inner diameter is 14.2 millimeter, inner diameter of the tube. Okay, now we have all these parameters: shell diameter, outer diameter of the tube, inner diameter of the tube, tube pitch, number of the tubes, number of passes, and length. Okay. Now, another parameters that we need to find is the baffle spacing and the number of baffles. How do we define that the baffle? How do we calculate the baffle spacing and number of baffles? So the criteria for the baffle spacing is that the baffle spacing maximum can be equal to the shell diameter. Maximum baffle spacing. So it can be equal to the shell diameter here. And the minimum baffle spacing can be shell diameter divided by 5. Shell diameter divided by 5. So now we have the limiting baffle spacing, that the minimum baffle spacing and the maximum baffle spacing that you can have, right? And if you keep your spacing minimum, then your number of baffles will be maximum. So what is the formula for the number of baffle calculation? NB. So we can go to the step. If you see on your page number, and I can show you on my lecture slides also, baffle spacing. What I did, yeah, here it is. Yeah, this is baffle spacing. So how do we calculate the baffle spacing? B is equal to length over number of baffle plus 1. So you note down this formula, that the baffle spacing B is equals to L over number of baffles plus 1. And when you switch this formula, then the number of baffles equals to L divided by B minus 1. Is it clear?
Yes.
Number of baffles equals to L divided by B minus 1. So this formula you have to use in your Excel to find out the number of baffles. So when we use the B minimum, it will give you the maximum baffle numbers. And when you use the maximum baffle spacing, it will give you the minimum number of baffles. So can you calculate this? NB and NB minimum, number of baffles minimum, and number of baffles maximum. Using this formula.
Doctor, the minimum is 28.7.
Correct.
Or 0.8.
Yeah, you using the minimum baffle spacing, that will give you maximum number of baffles.
Yes.
And
for the maximum,
yeah, very
4.9.
Yeah, so that is the minimum number of baffles, right?
Yes.
So now you have yes, tell me.
What is the baffle spacing that they want?
What is the baffle spacing? What they want? What do you mean?
We have to calculate the minimum number of baffles and maximum number of baffles,
Yeah.
right?
Yes.
So we need baffle spacing, right?
Yes.
Is it given in the question?
No, not given. We are setting up this parameter. So we take the constraint. What is constraint? That the maximum baffle spacing you can choose equal to your shell diameter, or minimum it can be 1/5 of shell diameter. So this is 1/5 and this is
Okay.
equal to the shell, right? So corresponding to
Yes.
this baffle spacing, how many number of baffles, which is 28.7, and corresponding to this baffle spacing, what is the number of baffles, which is this.
Okay.
Clear? So you can choose the number of baffles in between the two, either 4.95 to 28. But of course, you will choose the integer because it's a baffle, right? It cannot be in fraction. So from 5 to 28, you can choose any number of baffles. Is it clear?
Okay.
So
Yes.
initially I choose it 5, right? So when I decided my number of baffles integer fixed number 5, then I substituted 5 in this formula again to calculate my baffle spacing. So calculate
Okay.
the baffle spacing again using this formula. Now we fix the number of baffles as 5.
Okay. We fix it as 5 and we
And
found the baffle spacing to be 0.33.
yes, did you get this number 0.33 for baffle spacing?
5 plus 1.
Yes.
Yes.
Okay, good. So we got the baffle spacing. All right. Okay. And then we need to calculate the clearance, which we call it C, clearance.
Yes.
So what is the formula for clearance? The problem is that you have not watched the video, so everything I have to explain it twice. What is clearance? The clearance is spacing between the tubes, right? And for that, to find out the spacing between the tubes, if you can see this slide, that here we have this tube distribution, and you can see that what is clearance means. Can you see on the screen here?
Yes.
So you can see the clearance, right? So pitch and subtracted by the diameter of the tube. So you will get the clearance here. And clearance we are indicating by parameter C. So we calculated the clearance by subtracting from the pitch the diameter of the outer diameter of the tube. So this is what we get the clearance. Clear?
Yes.
Okay. And after that, we are calculating the tube side area. How do we calculate the tube side area? AT. AT. How do we calculate AT? You follow the formulation on page 472. Page 472 in your book, or you can open my slide, or you can open the book. Anything you can open. In my slides also it is explained, and in the book also. Page 472, step number D. You need to calculate AT. So the AT,
NT by multiplied by
yes,
the inner diameter
yeah,
square
yeah,
of
yeah,
4i.
yeah. Please calculate that and let me know how much is it.
Doctor, one thing I'm confused.
Yes, how much is AT?
Doctor,
Yes, tell me.
for the tube sizing, we need the BWG.
Yeah.
So how do we calculate BWG?
एक second, Hadi. BWG, it depends upon the strength, structure, what analysis. So for us, our course is not related to structure analysis. So we are just using what is the most common values like 13, 14, 15, 16, 17. So we can choose anyone. Because here strength
Okay.
requirement is not mentioned in the problem. So we choose 13 BWG and accordingly we choose the ID. Clear?
So, okay. Yes.
Okay.
But we have chosen 13,
Yeah.
but we chose the outer diameter to be 19.1, not 25.4.
The outer diameter is 3 by 1/4 inch. The 1 inch is the pitch.
No, I mean there is like two sizes. There is
There are two sizes.
3/4
So
inch
you,
and
yeah, there may be more sizes, but you have to choose your size. No? What is the point of
yeah,
there are
I
2 or
mean,
3 or 4 size? You have to choose your size, 3 by 4 inch.
is it what is required in the question or what exactly?
This is I explained in the beginning. Out of the 5 tables that we are choosing table 3.
No, this is another table.
Yes, this is another
This is
table.
for the tube.
No, what we selected this is our solution, right? 3 by 4
And
inch
this is
outer
for the
diameter.
okay.
Hmm?
Okay, so that is also the shell outer diameter. Okay,
Got it?
yes,
Clear? Or
yeah.
okay. So now we are getting the clearance. We got the clearance, and now we are getting the tube area. So did you calculate the tube area?
Yes.
How much is it?
7.12 to the power of -3.
Okay, fine. Yeah. And then the area for the shell side. Shell side area. Yes, Hadi, did you get the area? Tube side, shell side? Hello?
Uh,
Hello?
yes.
Anyone got the shell side area? Area for the shell?
Calculate. 0.0. Yeah, 0.02782.
Okay. Anyone else? Anyone else got the shell side area? This is, we are calculating from the formula at page number 472, step number D.
D.
Step number D, where it is given the formula for tube side area and shell side area. Hadi, are you there? Anyone else got the area? Salim?
Doctor, I was having internet connection, so I have just entered.
Okay. Okay, calculate the area.
Okay,
Anyone
now
else?
I'm doing.
Anyone else? Haytham, Ismail? You take the parameters from the screen.
Doctor, what is the value of P to BT?
The value of PT is this one, PT 0.0254.
0.02.
Yes.
Okay. wait.
Doctor, for the inside diameter of the tube.
Yeah.
Do we take it from the tube table?
Inside diameter of the tube. For
Yes.
the inside diameter of the tube, we get from the BWG table. We got it from the BWG table, right?
But
From this table, BWG. The
Oh,
outer diameter is 3 by 4. Inside diameter is 14.2 millimeter for
okay.
13 BWG. Yes, Hadi, I'm not listening from you. Are you calculating?
Maybe
No,
his-
doctor. I calculated, but I got wrong answers, so I got sad.
Yes, Sultan, what are you saying?
nothing. I understand.
Okay. Okay.
Doctor, 0.0027.
Okay. Yeah, 0.02783 meters square.
Yes. Yes.
Okay. And
Yes, doctor, I got some number.
okay, fine.
Doctor,
Yes,
this step in which page?
this table.
No,
Only-
step right now, the
Okay,
area.
the 472, page number 472.
Okay, thank you.
Page number 472, we have these all steps, right? Okay, so, and we need to calculate the heat transfer area later on, but I have just calculated it right here. Heat transfer area. What is the heat transfer area in this case for the shell and tube heat exchanger? How do we calculate heat transfer area?
From the outer diameter of the tube.
Okay.
That's right, doctor?
And multiply
Yeah.
by the number of tubes.
Number of tubes, pi dl. First of all, pi dl is the surface area of the one tube, right? Pi ODT multiplied by L and then multiplied by number of tubes.
Number
Yes.
of tubes.
Yeah, calculate how much is this. Pi ODTL multiplied by number of tubes.
What's the shell diameter, doctor? 336 millimeter.
The shell diameter is not using here. What do you want to calculate? AS?
Shell, yes.
Shell side area. Yeah, yeah, 3366, 336.6 millimeters the shell diameter.
0.6.
And
This one is 0.3366 meter.
Find the area 10.8.
Okay, good.
Doctor,
10.8.
what formula you used
For what?
to get a zero?
A0.
The heat transfer area. Yes.
A0.
What
This is the
form-
formula given in the step K. If you see the step K on page 473, A naught equals to number of tubes multiplied by pi ODT multiplied by L. Okay, so we got the A naught also, right? Then what is next? Because we got the areas, then we need to get the velocities. Step E, velocities, tube side velocity and shell side velocities. Find out that. Now you got the most of the idea of the shell and tube heat exchanger, because rest of the calculation is like calculating velocity, calculating Reynolds number, calculating Nusselt number, calculating overall heat transfer coefficient, and then calculating E, and then calculating final temperatures, like the same as in double pipe heat exchanger. The main difference was until the calculation of A. The main difference between the two, shell and tube and double pipe heat exchanger, was until the calculation of A naught, AT and AS, A naught. The rest of the calculation, you will see that it is just like double pipe heat exchanger. Anyway, did you get the VT and VS?
IT still does not come right.
What, AT?
Yes.
AT. So you can leave this step because it is explained in my slides also, that how to calculate AT. So you can ask this any other time, otherwise you will lag behind. So AT, just you can substitute in the formula and find out the values. Basically is given in page 472, step D is given, AT and AS, right?
Yeah.
So we substitute and we got these values. And then we
I
are calculating.
substitute what I did.
Yeah. Yes,
The
Hadi.
thing is that I did substitute, but I didn't get the same.
That's what I'm saying. You can recheck it any other time, because if I stuck one or two step, then other student will sit idle because they are calculating now V2, VT and VS. So
Okay.
if you stuck in any point, you can just move forward, because this is just simple calculation, straightforward substitution. It's nothing else, because the formula is given.
Okay.
And you just need to substitution. So maybe you just not substituting right value or something else, because
Okay.
it's simple substitution. And then calculate the
I see.
velocity, VT and VS.
Dr. VT,
Are you open the page 472, Hadi? Have you opened the page?
Yes.
Yeah. So
Yes.
yeah. So AT formula is like just substitution, simple substitution. Number of tubes multiplied by pi, IDT square divided by 4 divided by number of passes.
Yes.
Yeah, BT and VS. Anybody calculated VT and VS?
yes, doctor.
Is it matching?
Yes, 3.676.
Okay,
This
good.
is VT.
And VS?
0.9166.
0.9166. Good. So it's same. Now we need to calculate equivalent diameter. And remember that it is different for a square pitch and triangular pitch. It's different formula when we calculate the equivalent diameter. So what is given on page 472 is given for triangular pitch. In our case, it is, what is in our case?
Rectangle.
Yeah, rectangular pitch. So we need to use the square pitch formula. In our case, it is square pitch. So it is given on page 468. On page 468. DE. You got the formula for DE?
Yes, doctor.
Okay, good. For a square pitch distribution. So find out the DE.
Zero 0.023907.
Yeah, correct. So we got the DE also. Now we need to calculate RE for tube side and for shell side. So the formula again given on page 472 for Reynolds number, tube side and shell side.
Dr. R.
Yes.
Reynolds for the tube is 2.637.
Okay, good. 10 to power 4.
10 to the power minus 4, 4 plus
Plus
4.
4. Yeah. Yeah, good. Same answer as we got. Yeah.
Doctor, for Reynolds number S.
Reynolds number? Yes, what?
S 5.576.
10 power 4.
10 to 4.
Yes,
Power 4, yes.
good, very good. Same. Same. Very good. Yeah. Okay, so we got the Reynolds number and then we need to calculate the Nusselt numbers. Okay, so can I summarize the final solution now, because rest of the steps is almost same as like the double pipe heat exchanger. Okay, so we got the Reynolds number, and after the Reynolds number, like I'm taking the example from the previous another question. So as you can see here, can you see in my slide? I'm sharing my slide with you. Can you see that?
Yes.
Yes, doctor.
Yeah. So you got the Reynolds number for the tube side and you got the Reynolds number for the shell side, right? And then we can calculate the Nusselt number for the tube side. For the tube side, Nusselt number calculation is same as in the case of double pipe heat exchanger, and the expression you can take from the double pipe heat exchanger. For the shell side, Nusselt number, we have different expressions. So we will use this expression. It is mentioned in my slide also. This one we'll use. So we calculated the Nusselt number. After calculating the Nusselt number, we calculate the inner side heat transfer coefficient and then the tube side heat transfer coefficient. And then after we calculate overall heat, outer side or the shell side heat transfer coefficient. And then we calculate the overall heat transfer coefficient. And then we calculate A naught we already calculated. We calculate the C capacity ratio, minimum over maximum. So we already calculated these two in my Excel, and then we can then we calculate the number of transfer unit, and then we calculate E using this expression. And with the help of E, I find we calculate the temperature. We calculate the temperature, that is where is that? Sorry. We calculate the final temperature T2 and T2. So this is the procedure, so that you have to follow. Okay, so you have reached until the Reynolds number. So you keep doing, finding the Nusselt number and Nusselt number for the shell side, tube side, right? And then heat transfer coefficient. Okay, so keep doing it. The meeting will be end in 4-5 minutes. Then we will connect again. Okay. So anybody who got the answer for Nusselt number for tube side, shell side, just share with me. So for the tube side, you need to follow the step H on page 473.
Doctor?
Yeah.
Here on the table, why do we have two equivalent diameters?
Because we always calculating equivalent diameter. What else do you want?
No, I mean, why two values?
Why?
Why do we have two values for equivalent diameter? There are two rows.
There are two values. No, the second row is second iteration. Second row is second iteration.
Okay.
So you don't need to worry about that. Second row is my second iteration.
Because I calculated the E, I got it to be 0.02407.
So you use the second row values.
No, I didn't use second row values.
Anyone else
I used
calculated
literally-
DE? Let me listen from other student. Anyone else calculated DE? Yeah, DE, they already told me this. They got this. You may be doing mistake, Hadi, somewhere. Either you taking the value from
because,
second row or something else.
No, I used the formula on page 468.
Yeah, but this other student also used the same formula. They got the answer 0.02391.
Okay, outer diameter is 3/4 inch, right?
Outer diameter is 3/4 inch, but it looks very much same. Like it's not much difference. 0.239 and 0.240 is almost same. 293 millimeter. Oh, sorry, 23.9 millimeter and 24 millimeter is almost same, Hadi. It's just maybe your calculate. Somebody using a certain digit will make this difference. It's almost same.
I see.
Anyone else moving forward? Calculated Nusselt number, tube side, shell side. Nobody responding.
For shell side, I get 224.
240 shell side.
24, I get it. 224.
Which formula you use?
For turbulent flow, 0.023.
No, shell side is not turbulent flow. Shell side formula is different. You see on my screen? Shell side formula is different.
Yes.
For tube side, we use the same formula, turbulent flow. But for the shell side, the formula is different.
Yes, doctor.
Yeah. The shell side formula, the formula is
0.36.
Yeah, 0.36, correct, for shell side.
For tube side, doctor.